Good afternoon, everyone. My topic for this afternoon is about characterize the invertibility of a matrix using the invertible matrix theorem. I am Jessel P. Palermo, and I will be your discussant for this topic. So, invertible matrix theorem. So this theorem basically summarizes all the other theorems that was being discussed by the previous presenters. And this theorem also contains statements that are also equivalent with one another. Next slide. Okay, so the invertible matrix theorem. So it says that given some n by n square matrix, then the statements or the following statements are equivalent. So if one is true, then all the other statements is true or are true. And if one is false, then all the other statements are false. So this theorem separates the set of all possible n by n matrices into two groups. So what are these groups? So first we have the singular matrices which are non-invertible, and we have the non-singular matrices which are invertible. So if the statements are all true or are true, so you are in the non-singular matrices which are invertible. And if your statements are false or they are all false, then you are in the singular matrices which are non-invertible. Okay. So let's start with letter A. So A is an invertible matrix. So remember that when you find the inverse of A when you find the inverse of A, you are setting a matrix where you have A, this one, A, and you have an identity matrix of the same size. So in this case, we use the 3 by 3 as an example. So then we row reduce, and if you're able to turn the left side of the augmented matrix into the identity matrix, then the right side through those row operations becomes the inverse. So if we're able to perform row operations, becomes the inverse, and turn the left side into the identity matrix. So the right side gives us the inverse, and this is what happens when A is invertible. So ito yun siya. Then next, okay, so these three, by the way, these three statements are interconnected with each other. So say for example, A is invertible, so A implies B. So we cannot solve an invertible matrix without going to row reduction. So this letter B here, A is a row equivalent to identity matrix. Okay. So the next we have B. Yes. A is row equivalent to identity. If you noticed, when we find the inverse here, the first, we find the inverse, we do the row reduce. We do the row reduce until we form the identity matrix. So we can say that A implies B. Okay, and let's proceed to letter C. A has n pivot positions. So A has a pivot positions. By following the steps, a while ago we did the letter A, which is A is an invertible matrix. Then next we have the row reduction, and by following the steps, we will end up with every pivot in every column, in every row. When we do the row reduce to the identity matrix, which gives us C. So these three here are interconnected with each other. Okay, so letter D. So letter D, the equation AX is equal to 0 has only the trivial solution, because anytime you're able to row reduce A to the A to the identity matrix. For instance, we say A here is our matrix, and we have here columns of zeros, and after doing a lot of operations here, and we just assume, let's just assume that A here is invertible, so we can reduce this one to the identity matrix. So after all, these row operations will leave this. Okay, so we have row operations here. This will leave these 0 here, these zero entries as zeros. So this column will remain zeros. So that's how we get the equation AX equals 0 has only the trivial solution. And for letter E, the columns of A form a linearly independent set. Okay, so the columns of A form a linearly independent set. So if you remember how to determine if a collection of vectors is linearly independent, we would set them up as columns of a matrix, just like this one, but differently. Columns of a matrix, and we row reduce to form where we would only have a trivial solution. So we would have a linearly independent set. So this is letter E. And for letter F, we have the linear transformation is 1-to-1. So when can we say that it is 1-to-1? So 1-to-1 linear transformation. So there is exactly one vector X that gets sent to the vector B, that is AX. So this equation AX equals B has a unique solution. That is when the transformation is 1-to-1. Okay, so letter F here and our letter G here are closely tied. So the equation AX equals B has at least one solution for each B in Rn. So they are just related to each other. And for letter H, we have A span. The columns of A, let's go back. Okay. The columns of A span Rn. So A span Rn, we can take any vector in Rn. So any n dimensional vector will we'll call that B, can express B as a linear combination of columns of A. So where basically here in letter H, we are just also creating another AX is equal to B, which has a solution, a unique solution. So parang related lang din sila. And for letter I, the linear transformation is maps Rn onto Rn. So we have the previous reporter discussed this one, that is ano ba yung onto? Okay, so when you row reduce a matrix A, if A is the standard matrix for a linear transformation, if there is a pivot or a pivot in every row, then the transformation is onto. So it's different from 1 to 1 because 1 to 1 has a specific solution, but here in onto we have pivot in every row and in every column. And remember that if we have a pivot, then the matrix is invertible. Okay, so examples and illustrations. So I have here examples. So is this matrix invertible? Okay, so we have here the solution. We have here A and the values of our matrix. Okay, so for the solution, so the second column is the multiple of the first, and the columns are linearly independent or linearly dependent. So A does not satisfy the condition in letter E. Ano ba yung condition in letter E? So in letter E, the columns of A form a linearly independent set. But here in our example, our second column here is a multiple. So if it is a multiple, then it is linearly dependent. So this matrix here is not invertible. Okay, next, we have let A be a 3 by 3 matrix such that A, so our first matrix is A. So meron siyang, in the column we have 1, 7, and 0. Then the other one we have 2, 0, and negative 1. So show that the rank of A is at most 2. Okay, so solution. If we set B is equal to A, we have here the values is equal to A, 2, 0, and negative 1. So then AX is equal to B has multiple solutions. So it does not satisfy condition 6 of the invertible theorem. So therefore, it does not satisfy condition 5. So the columns of A do not span R3. So R3 kasi 3 by 3. Therefore, the column space has dimension strictly less than 3. The rank is at most 2. Okay, so take note. So to reiterate, the invertible matrix theorem means that there are two kinds of square matrices. And the first one, we have invertible matrices, and number 2, we have the non-invertible matrices. So for invertible matrices, all of the statements of the invertible matrix theorem are true. And for non-invertible matrices, all of the statements of the invertible matrix theorem are false. Okay. So take note that these statements here in our invertible matrix theorem, if only one statement is true, all the rest of these statements are also true. And if there is a false statement, say for example, A here will be false, we can have a matrix that is not invertible, then all of the following statements are also false. So these will not, or these we cannot consider it as invertible if letter A pa lang false na, so the rest will also become false. Okay, so that should be all, and thank you very much for listening to my topic.